The Algorithmic Foundations of Computer Science. A deep dive into logic, computation, and innovation in an era where algorithms shape our digital universe. From search engines that predict our needs to autonomous vehicles navigating complex streets, understanding the core principles of computer science has never been more vital. This exploration delves beyond surface-level knowledge, uncovering how computational logic forms the backbone of modern technology. Computer science is not merely about coding, it's the study of problem-solving through systematic methods, data structures, and theoretical frameworks. From quantum computing breakthroughs to AI ethics debates, we'll unravel its multifaceted nature in ways tailored specifically for those who thrive on algorithmic challenges. The birth of modern computing. Tracing historical milestones, the journey began in the 19th century with Charles Babbage's conceptualization of the analytical engine, a mechanical general-purpose computer that laid the groundwork for future innovations. Though never fully built during his lifetime, its design included key elements still relevant today: memory storage units and input-output mechanisms. Babbage's collaboration with Ada Lovelace marked a pivotal moment. As the first programmer, she developed instructions for calculating Bernoulli numbers using punch cards, an early form of software engineering. Their work established fundamental concepts of computation that persist across centuries. Fast forward to 1936 when Alan Turing introduced the concept of the universal Turing machine. This theoretical model demonstrated that any algorithm could be executed by a single machine given enough time and memory, revolutionizing both mathematics and computer science foundations. Turing's ideas led directly to the development of programmable computers in the mid-20th century. John von Neumann's architecture provided practical implementation paths, creating systems that could store programs in memory rather than relying solely on external hardware configurations. ENIAC, completed in 1945, it was the world's first general-purpose electronic computer capable of being reprogrammed to solve various problems. UNIVAC I, commercially available in 1951, it became the first successful commercial computer used for business applications. Core principles that define computer science: at its heart lies computational theory, the mathematical foundation that defines what can and cannot be computed efficiently. This includes complexity classes like P versus NP, which have profound implications for cryptography, optimization, and artificial intelligence research domains. Data representation forms another cornerstone principle. Understanding binary systems, hexadecimal encoding, and ASCII/Unicode character sets enables developers to manipulate information at its most fundamental level while optimizing system performance across diverse platforms. Algorithms constitute perhaps the most crucial aspect of computer science education. They are step-by-step procedures designed to solve particular problems efficiently, often measured against parameters such as time complexity, O, N, and space requirements. Efficient algorithm design remains central to technological progress. Consider sorting techniques, from naive bubble sort implementations, O, N superscript 2, to advanced quicksort variants achieving average case efficiency around O, N log N. Choosing appropriate algorithms directly impacts real-world application scalability. Modern applications shaping our world today: distributed computing networks power global infrastructure, enabling services ranging from cloud storage solutions to blockchain technologies securing financial transactions worldwide. These systems rely heavily on consensus protocols, ensuring reliability despite potential network failures or malicious actors attempting attacks. Machine learning has become ubiquitous, transforming industries through pattern recognition capabilities powered by neural networks trained on vast datasets. Techniques like gradient descent optimize weights within these models, allowing them to make increasingly accurate predictions over time. Cybersecurity represents another critical domain influenced by continuous advancements in computer science research. Encryption standards evolve alongside threats, necessitating ongoing innovation in public key cryptography and secure communication channels protecting sensitive user data globally. Quantum computing promises revolutionary changes by leveraging superposition states and entanglement properties inherent in subatomic particles. While still largely experimental, prototypes demonstrate potential for solving certain types of problems exponentially faster than classical counterparts. The future landscape, emerging trends and challenges as we look ahead. Several trends are shaping tomorrow's technological landscape. Edge computing aims to reduce latency issues by processing data closer to sources instead of sending everything back to centralized servers for analysis. Artificial General Intelligence, AGI, presents both exciting opportunities and ethical dilemmas regarding control mechanisms necessary to ensure safe deployment without unintended consequences affecting society negatively. Sustainable computing initiatives focus on minimizing energy consumption associated with massive data centers housing countless servers running continuously day and night worldwide. Innovations here include liquid cooling systems and renewable energy integration strategies, reducing carbon footprints significantly. Evolving regulations surrounding AI usage require careful consideration when developing new technologies involving automated decision-making processes impacting human lives substantially, including areas like hiring practices or judicial sentencing recommendations based purely on algorithmic outputs. Programming languages, tools for expressing computational ideas. Selecting appropriate programming languages depends largely upon project requirements and desired outcomes. Low-level languages provide direct access to hardware components but demand greater expertise managing resources manually compared to high-level alternatives abstracted away much complexity automatically. Functional programming paradigms emphasize immutability and pure functions producing consistent results regardless of execution context. Languages like Haskell exemplify these principles, promoting code clarity while facilitating parallelism naturally due to absence of side effects typically found elsewhere. Object-oriented approaches organize code around reusable objects, encapsulating related behaviors and attributes together. Java and C++ remain popular choices owing partly to their extensive libraries supporting enterprise-scale development projects effectively. TypeScript introduces static typing features enhancing JavaScript flexibility, initially intended primarily for web front-end interfaces. Its popularity reflects growing need among developers seeking improved maintainability benefits, especially within larger teams collaborating simultaneously. Software development methodologies, evolving practices in industry agriculture used to follow traditional waterfall models emphasizing sequential phases before moving on to next stage once previous completed successfully. However, iterative methodologies gained traction, offering advantages particularly suited agile environments requiring frequent adjustments based on stakeholder feedback loops. Scrum framework organizes work into sprints lasting usually 2 weeks, focusing tightly aligned goals achieved collaboratively by cross-functional teams working closely under guidance from product owners, defining priorities clearly each cycle. Kanban visualizes workflow progression using boards divided between to-do, in progress, and done columns, helping identify bottlenecks quickly so they may be resolved promptly, maintaining smooth operations consistently throughout entire organization. DevOps culture integrates development and operational activities, fostering continual delivery pipelines, automating testing procedures prior release, ensuring quality maintained reliably without compromising speed, essential competitive advantage nowadays. Educational pathways into computer science professions. Pursuing formal degrees provides structured curriculum covering foundational topics including discrete math, operating systems internals, database management principles, etc., preparing students comprehensively entering workforce confidently equipped handling technical challenges encountered professionally. Boot camps offer accelerated training focused intensively on practical skills applicable immediately post-completion, contrasting university experience centered more broadly toward theoretical understanding supplemented occasionally applied exercises reinforcing concepts learned academically. Online courses through platforms like Coursera or edX enable self-paced learning accessible remotely anytime, anywhere, making education more inclusive, reaching demographics otherwise unable to attend physical institutions traditionally. Certifications validate proficiency attained through specialized examinations demonstrating mastery particular tools or frameworks. Employers seek actively recruiting candidates possessing credentials showing competence required job roles effectively. The role of ethics in technological advancement. With increasing reliance upon digital ecosystems governing nearly every facet daily existence comes responsibility addressing moral concerns arising inevitably alongside rapid innovation. Trajectories accelerating continuously now. Bias embedded unintentionally within datasets utilized train machine learning models risks perpetuating societal inequalities and less carefully monitored mitigated proactively implementing safeguards preventing discriminatory outcomes, harming vulnerable populations disproportionately affected adversely. Privacy considerations grow ever more significant as personal information collected extensively analyzed leveraged commercially often without explicit consent granted freely assuming users aware extent data harvested utilized subsequently. Environmental impact assessments evaluate ecological footprint generated manufacturing disposing electronic devices consuming substantial amounts electricity powering data centers globally contributing considerably towards climate change exacerbated further expansion virtual realities demanding higher computational capacities sustainably managing resources becomes imperative challenge confronting industry leaders urgently. Conclusion. This deep dive into computer science reveals its intricate relationship with virtually all aspects contemporary life shaped fundamentally through algorithmic ingenuity driving relentless pursuit pushing boundaries continuously expanding possibilities envisioned previously unimaginable. To stay ahead in this dynamic field requires embracing lifelong learning mindset, engaging actively communities, exchanging knowledge, regularly exploring emerging technologies, keeping abreast developments, influencing direction, discipline, shaping future generations. HTML